Welcome to my presentation, which I will talk about iron-carbon phase diagram. So let's just get to it. The iron-carbon phase diagram tells us exactly what state our metal is in at any given temperature and composition. On the y-axis, we have temperature. On the x-axis, we have the weight percentage of carbon, usually going up to 6.67%, which is the limit for cementite. Also, the key point here is the diagram represents equilibrium. So it's important to note that. And then we have three primary phases, which is ferrite, austenite, and then cementite. The ferrite is stable at room temperature. It's soft, ductile, and can only hold a tiny amount of carbon, just 0.022%. And then we have austenite. It is a high temperature phase. It has a face-centered cubic structure, which is shortened by FCC, allowing it to soak up much more carbon, up to 2.14%. And then we have cementite. This is also called iron carbide. It's an intermetallic compound that is incredibly hard and brittle. Most of our engineering goals involve balancing these phases. And then we have the eutectoid point. It's at 0.76% carbon and 727 Celsius degrees. It is basically when you cool austenite enough through this point, it transforms directly into a two-phase solid called perlite. Perlite looks like a sandwich of alternating layers of ferrite and cementite. This lamellar structure is what gives construction steel its unique balance of strength and toughness. If we have less carbon, we call it hypoeutectoid. If we have more, it's hypereutectoid. And then let's talk about the steel versus cast iron. The difference is this vertical single line. It is what parts steel and cast iron. If our iron has less than 2.14% carbon, it's iron. If it has more, it's basically cast iron. And what's the difference? Well, basically cast irons are less rigid and other stuff we will hear throughout our years in material engineering. But basically, cast irons undergo a different reaction at higher temperatures called the eutectoid reaction, where liquid transforms into a mixture of austenite and cementite called lydobrite. And as conclusion, we can just say that by mastering this diagram, engineers can design a metal's properties just by changing its carbon content or its heat treatment. It is the foundation of modern metallurgy.